Hello and welcome to this video for Chemistry 30. This is Miss Simpson, and this is something that we're going to do in the equilibrium unit, looking at something called ice tables, sometimes also called rice tables. Okay, so I'm going to explain what a rice or ice table is and what the purpose of it is and how you know when to use it. So if you're given a question and you are given the initial concentrations of substances that are reacting, and we are looking for Kc, it's important to note that we need to know the equilibrium concentrations of everything in order to find the Kc or calculate the Kc. So this is what the purpose of a rice or ice table is for. Now the R in the rice table, if we use that, stands for having a balanced reaction. Let me try spelling that again. Reaction. We always need to start with a balanced reaction, okay? And then the I in the ice table stands for the initial concentration of everything. The C stands for the change that everything goes through, and the E stands for the final or equilibrium concentrations. Now, this relies on understanding that in a chemical reaction, everything reacts and is produced in stoichiometric quantities. So this means we're going to be doing some stoich calculations in here, and the products always increase. So the change the products are going through will always be, they will be going up. And the change the reactants will be going through is they will always be going down. Okay, reactants in a reaction usually, or like most of the time, we can say all the time, are going to be used up and their concentrations will go down, whereas the products are being made, so their concentrations will increase. Again, we're doing this because in order to solve for Kc, we need to know the equilibrium concentrations. Remember, again, square brackets here means concentrations. So we need to know what is the concentration after the reaction has gone to completion, after it's now reacting in the forward and reverse process at equal rates, so that it appears the reaction has stopped. So we have a few examples. Let's say you're told we have hydrogen iodide gas decomposing. So hydrogen iodide would be Hi, and this is a gas. If it's decomposing, it's my only reactant, and it's making hydrogen, which is diatomic by itself, and iodine, which is also diatomic by itself. It's telling you that these are gases. Iodine is normally a solid at room temperature, but it's telling you here gas. Now to balance this, I would need a 2 and 1s, and we want to have balancing coefficients because that's what's needed for our stoich. So we have our reaction written down. So we could, like I said, call this a rice table, or we have our reaction, our initial concentrations of everything, the change that everything is going through, and then we are going to be left with the final or equilibrium concentrations. Now, very important, this chart needs concentrations. We're dealing with concentrations. So if you're given moles and volume, take your moles, divide by your volume. Now in this case it's 1 liter, and we get an answer of 2.00 moles per liter. That is the amount of Hi being placed in the container. So that is my initial concentration of Hi. Okay. If the question doesn't tell you there's any products, we can assume to start that there are none. Okay, unless it tells you you have some, you're starting with none. Now we are told that the final or equilibrium concentration of H2 is 0.214. So that is this value down here, 0.214 moles per liter. Again, if you were given moles there, you would divide by your volume to get concentration. Now, I have enough information to find the change that my hydrogen gas is going through. I know it started at 0 and it ended at 0.214. So that means the change was that, and I'm going to call this my concentration given. The change is that it went up by 0.214 moles per liter. Okay, so this is my given. I was given its equilibrium concentration. I knew its initial, so I found the change. I'm going to do that to my other species of my reaction. So let's find my other product first. So I know the concentration change that my iodine is going to go through. It's a product, so it's also going up. Products always go up by 0.214 times wanted over given. My wanted over given ratio here is 1/1. So my iodine is also going to increase by 0.214 moles per liter. It started also at 0. So at equilibrium, or once the reaction has gone to completion, I will also have 0.214 moles per liter of my iodine gas. Now, for my reactant, it is also a wanted. This is going to go down by 0.214 times wanted over given is 2/1. So the change that the HI is going to go through, 0.214 times 2, is it's going to go down by 0.428 moles per liter. Again, products always go up, reactants always go down. Okay, so now I take my initial concentration, I apply the change. The change is to subtract because it's going down. So 2 minus 0.428 gives me an equilibrium concentration for my HI of 1.572 moles per liter. Okay, so again, you take the initial, apply the change. For the HI, it is to subtract 0.428 from the initial of 2, and that's how we are left with our equilibrium concentration for everything. So now I can find my Kc. If I write my expression without putting any numbers in, it would be my hydrogen gas. It's always products over reactants. My iodine gas. These have no exponents because they have no balancing coefficients, or you can say they have an exponent of 1 if you wanted to. Over HI gas, which does have an exponent of 2 because it has a balancing coefficient of 2. So if I put my values in, my hydrogen is 0.214 moles per liter. I'm going to skip my units. My iodine is 0.214. And my HI is 1.572, and I need to square that. So if I put this into my calculator, 0.214 times 0.214 divided by 1.572 squared gives us an answer. It looks like we can have 3 sig digs. The temperature is not used in the calculation, so it doesn't affect our sig digs. We use the numbers that we were using in the calculation. So I can have 3 sig digs, 0.0185. Now remember also there are no units with Kc. It's just an equilibrium constant. Okay? So that is our first example. Again, starting with the initial concentrations of everything, the equilibrium of one substance, so we can be given the change of one substance to find the change of the others, and then take the initials and apply the change to get the equilibrium. Let's look at another example. So let's say we have a 500 milliliter, I'm going to need to convert that into liters, is reacting in a reaction vessel. We have carbon monoxide and water vapor reacting to produce carbon dioxide and hydrogen gas. So if I start with my reaction, I have CO gas reacting with water vapor, which would be H2O gas. We are producing CO2 gas and hydrogen, which is diatomic. Now this reaction, everything is balanced. So I just need ones for everything, but always double check. And then again, we're going to do I, C, and then finally E so that we can find KC. Okay, I like drawing lines here, just showing again my stoichiometric quantities. I'm treating the reaction like the heading of a chart. So I am told the technician injects 2 moles of both reactants into the container. And remember, our volume needs to be converted into liters. So that would be 2.00 moles divided by 0.500 liters. Okay, so we get an initial concentration of my 2 reactants to be 4.00 moles per liter for both of the reactants, because it says that's the amount of both they injected. And again, we're not given any products, so we can assume they're starting at 0. Now it says that at equilibrium, the concentration of remaining CO is 1.31 moles per liter. So this time I am given the amount of this reactant so that I can find the change and make that the given change, given concentration. So if it started at 4, if I subtract 1.31, this means that it has gone down because it's a reactant by 2.69 moles per liter. Okay? And then everything else again becomes a wanted to find their relative change. Okay, my water vapor is also going to go down because it's a reactant, and its wanted over given is 1/1. So it is also going to go down by 2.69 moles per liter. It started at 4. I'm going to apply the change, which is to subtract 2.69. So I'm left with 1.31 moles per liter of my water vapor. My products are going to go up by the given change times wanted over given. So both of them are going to go up by 2.69 times 1/1. So they're both going to go up by 2.69 moles per liter. Products, again, always go up. Reactants always go down. Okay? I'm starting at 0. I apply the change of an increase of 2.69. So that means at equilibrium, both of my products, because they're starting both at 0 and they're going through the same change, so both of them are going to end at 2.69 moles per liter. Now my Kc expression, products over reactants, everything has a balancing coefficient of 1. So nothing has any exponents. So it'll be 2.69 over 1.31. Now if you're putting this in brackets in one step, make sure you have a bracket around your entire denominator. So 2.69 times 2.69 divided by 1.31 times 1.31, we get an answer to 3 sig digs of 4.22. Okay? So again, very similar to the last example, we have the initials of everything, the equilibrium of one thing to find the given change, and then we can apply wanted over given to find the change of everything else. Again, remembering that reactants are decreasing by that change, and the products are increasing, or you're adding the change. Okay? Now the next example is a little different. We are told that we have gaseous phosphorus pentachloride decomposing into phosphorus trichloride and chlorine gas. We are given Kc. We are given the initial amount of our reactants again, and asked to find the equilibrium concentration of each species. So we're not asked for Kc this time, and we're not given the equilibrium concentration of anything. We have to find all of them, okay? It still requires an ice table or a rice table. Our reaction, phosphorus pentachloride would be PCl5, penta being 5, is decomposing into phosphorus trichloride, that would be PCl3 gas, and chlorine is diatomic also. Now I'm going to have a balanced reaction again of all ones, and I'm going to do the rest of my ICE table. Okay? So I'm starting again with a mole value of my reactant. So I need to divide by the volume to get concentration. This would be 1.00 moles per liter. So that is my initial concentration. Oh, sorry, my pen sometimes likes to make these wonky horizontal lines. Okay, so my initial concentration of my reactant is 1.00 moles per liter. And we'll assume, again, because we're not told otherwise, we are starting with no products. Now, that's all we have other than the Kc, okay? So what I'm going to do is I'm going to say that I know my reactants are going down by a certain value. The value is also relative to its balancing coefficient. So if I have a balancing coefficient of 1 here, it's going to go down by 1x. I'm going to call the changes going through x. Okay? If that was a balancing coefficient of 2, it would be going down by 2x. So the 1x, the 1 is irrelevant, right? But it helps us, again, in case the balancing coefficients were 2, we'd have to apply that. Now my products are going up by 1x because their balancing coefficients are 1. So if I kind of apply this to get an equilibrium, I'm going to have 1.00 minus 1x, which I'll just call x. My products will be 0 plus 1x, which will equal x, and 0 plus 1x will also equal x. So if I put this into my Kc expression, and I know what my Kc is, I know my Kc is 1.00 times 10 to the negative 3 equals my products. Again, nothing has any exponents on it because there's no balancing coefficients. And I need to solve for x. So at this point, if I were to solve for x, I would have to use the quadratic formula, and it is given in your Chem 30 data booklet. However, all of these questions are always going to allow you to do an approximation method. Now, the rule for the approximation method says that if the concentrations are 1,000 times greater than the Kc value, the equilibrium constant, we can say that x is very, 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 very small, so that my 1 minus x on the bottom can be simplified to just 1. So I'm essentially omitting or simplifying by omitting the x on the bottom. So instead of 1 minus x, it's just 1. My other x's remain, okay? So if I go back to that formula, I can now use this approximation method. And like I said, you'll always be able to use this approximation method in Chem 30. So we're going to cancel that. And so we're going to get left with 1.00 times 10 to the negative 3. If I simplify this, equals x squared over 1.00. So now all I have to do, a lot easier solving for x, if I multiply by my denominator, that's obviously going to equal the same number. And then I'll get equals x squared. So to solve for x, I just need to square root. Okay, so once I solve for x, now that's not quite a question done once I solve for x. So second square root 1 times 10 to the negative 3. Oops, I made a mistake there. Oh, I made a mistake again. second square root 1 times 10 to the negative 3. There we go. X equals 0.03162, so on. This is my X. Now I can put it back into my equations for the equilibrium concentrations of everything. I'm just going to erase this to have a little bit more space. Okay, so my equilibrium concentration of the PCl5 is 1.00 minus, now I know what X is, 0.3162. So if I apply that, 1 minus that answer, I'm allowed 3 sig digs, so 0.968. These are concentrations, so they do have units. And now my other two products are just X. So if I round X to 3 sig digs, it would be 0.0316 moles per liter for each of my two products. And my pen did that funny line again. And that is it. So those are your equilibrium concentrations. This is PCl5, this is PCl3, and this is Cl2. Okay? So those are the other ways of doing ice table questions when you're given the equilibrium constant and asked to find the equilibrium concentration of everything by being given only the initials. So you have to use this X method and solve for X. Now I do have a sample diploma question. I'm just going to pop up the answer so that if you're trying this for homework, this is not the X method that we just did. You are given the initial moles and volume of your system. So you're given the initial concentrations of everything, the equilibrium concentration of one of them, so you can solve for KC. And you should get 0.566 if you give that a try. Okay? And that is it for this video. Thank you very much for watching.